In topic 2, we're going to be looking at price competition. The basic model of price competition is called the Bertrand model. We'll use this model as the basis for extensions, so it's essential that you understand this model. So far we've looked at monopoly. Now we're going to be looking at cases where we have more than one firm, and when there are multiple firms, we need to worry about whether the firms are choosing price or quantity. So in the Bertrand model, we assume they choose price. There is also something called the Corno model where they choose quantity. So in order to model a situation with a few firms, we need to use game theory because the choices of the firms are interdependent. So what that means is that each firm's best choice of price depends on the other firm's choice of price. So in the Bertrand model, with two firms, we're going to call the firms A and B. There's a homogeneous good. All the consumers care about is price. They buy from the firm with the lower price. If the prices are equal, then the total demand is shared equally between the two firms. And the total demand for the good is D of P, where P is the lower of the two prices. D, that's our demand function. So here the market demand function could look like a normal demand curve, downward sloping. So here's D of P. Or it could look something like this, where each consumer has a maximum they're willing to pay. If the price is less than or equal to that amount, then they purchase 1 unit. So here I've drawn a demand curve where there's a total consumer of 1, but this 1, we could multiply that by n if we've got n consumers. We're going to be able to cover all sorts of cases. It doesn't have to be a smooth demand curve. It can look like the demand curve on the right. Each firm has a constant marginal cost C. So all we assume about C is that it's not too high. It's below the intercept of the demand curve. So in the model, each firm sets prices simultaneously. The prices are PA and PB. So this is a simultaneous move game with two firms. Each firm's goal is to maximize its profits. So in order to solve this model, in order to find the equilibrium prices, we use game theory. We're looking for a Nash equilibrium. And in Nash equilibrium, each firm plays a best response. So a best response of a player to the other player's strategies in the game is a strategy which gives at least a higher payoff as any other strategy. So in the Bertrand game, each firm's strategy is a price. A best response of firm A to a price chosen by firm B is a price that gives A at least a higher profit as any other price. A Nash equilibrium is where each player is playing a best response to the other player's strategies. Another way to think of this, in a Nash equilibrium, there is no incentive for any player to deviate given the other player's strategies. No player has a strictly profitable unilateral deviation. If they were to change their strategy, but all other players kept their strategy the same, that's a unilateral deviation. In the Bertrand game, a Nash equilibrium is a pair of prices, PA star, PB star, such that each price is a best response to the other price. In the Bertrand game, we have a Nash equilibrium if given B's choice of price, PB star, there is no price, PA, which gives a higher profit than PA star. So before we consider the full game, let's consider a simplified version of the Bertrand game. We'll consider a game where they can just choose 3 price levels, 3, 4, or 5. So in the example here, I have what's called a payoff matrix. We have firm A, we have firm B, we have each of their strategies listed. So firm A here is the row player, firm B is the column player. We have their payoffs, which are the profits. So firm A's profit is listed first. The row player's payoff is always listed first. And here I've also put the numbers at different heights. So column player firm B's payoff is higher and to the right. So we have the two firms' profit for each combination of the prices, and we're going to look for a Nash equilibrium. So in order to find the Nash equilibrium, let's do it by finding the best responses. So I'll underline the best responses of firm A using a red line. So let's look at firm A. What price should it charge if firm B chooses a price of 5? So what we have to do is look along this line here and find the highest number, the highest profit for firm A when firm B chooses a price of 5. and the highest number here is 14. So the best response of firm A to firm B, choosing a price of 5, is a price of 4. What if firm B chooses a price of 4? Well, then the highest number here is 8. And if firm B chooses a price of 3, then the highest number here is 4. So firm A should choose a price of 3. Now we can do the same thing for firm B. I'll underline the highest payoff for firm B in blue. So because the game is symmetric, it's going to be very similar. The highest number here is 14. The highest number here is 8. And the highest number here is 4. So we have the best responses. The best response here is to charge a price lower than the other firm, if they can. When the other firm prices at 3, they can't lower their price here, so they end up charging the same price. So the Nash equilibrium here is where they both price at 3. So those are the Nash equilibrium strategies. And then the payoffs, the profits, are equal to 4 for each firm. So if you're asked for the Nash equilibrium, you should give the strategies. If you're asked for the Nash equilibrium payoffs, you should give also the payoffs. So another way to see that this is the Nash equilibrium is to check there's no incentive for either firm to deviate unilaterally. So let's think about this combination of prices. Is there any incentive for either firm to change their price? Well, let's look at firm A. They're charging a price of 3. If they change their price to 4, they're going to get no demand and no profit. The same thing if they price at 5. So here, they can't do any better than pricing at 3. There's no strictly profitable unilateral deviation. Whereas if you look at any other combination of prices, there is a strictly profitable unilateral deviation. So if you look at where they're both pricing at 4, if firm A lowers its price from 4 to 3, it's going to increase its profit from 7 to 8. So this cannot be a Nash equilibrium. So another way to find Nash equilibrium is to check all possible combinations of prices and find the ones where there's no incentive for either firm to deviate unilaterally. Now, in the Bertrand model, we don't allow just a few prices or a finite number of prices. Firms can choose any price greater than or equal to 0. So we can't use a payoff matrix to represent the game. We're going to have to use instead payoff functions. So we have profit functions pi A and pi B, which are functions over pairs of prices. So in the game with 3 prices, we had, for example, that the profit of firm A, when its price was 4 and the other firm's price was 5, is 14. At those prices, the profit of firm B is 0. So in the general case, the profit of firm A, when its price is PA, the other firm's price is PB, is just given by the profit per unit, PA minus the marginal cost, multiplied by the demand of firm A. And the demand of firm A here depends on both firms' prices. So this is what's different here compared to the case of monopoly. So the demand of firm A, it's going to be 0 if its price is bigger than the other firm's. It's going to be the market demand at its price if its price is less than the other firm's. And if the prices are equal, then they share the demand equally. Now you might be wondering, where did the numbers in this payoff matrix come from? Well, they came from the case where C is equal to 2 and the market demand function is 11 minus P. So the demand of firm A, when its price is 4 and the other firm's price is 5, if we look at the demand function, it's going to be the market demand at a price of 4, which is 11 minus 4, which is 7. And the profit then of firm A, when its price is 4 and the other firm's price is 5, is going to be the price of 4 minus the marginal cost multiplied by that demand, which is 14. In this diagram, we're going to draw the demand curve of firm A given some price of firm B. So let's suppose firm B's price is here. And let's find firm A's demand curve. So in the diagram, I have the market demand curve, the straight line, which we're drawing against firm A's price. So if firm A was the only firm, this would be its demand curve. But it's not the only firm. if it prices above firm B's price, then it's going to get no demand. So if it prices above PB, then its demand is 0. So the open circle here means that this point is not part of the demand curve. Now what if firm A prices below PB? Then it gets all the demand. Its demand is just the market demand. Now what if firm A prices at PB? Well, then they share the demand equally. They get half of the market demand each at this price PB. So its demand is halfway between this point and this point. So this point here is D of PB, and this point here is half D of PB. So this red line is the demand curve of firm A. It's a function of its price and the other firm's price, and we've drawn it for a particular value of PB. As we change PB, this point here will move and the demand curve for firm A will change. So this is A's demand curve given a fixed price of firm B. So now we want to calculate the Nash equilibrium of the full Bertrand model. So recall, there are two ways to find the Nash equilibria. We could do it by finding the best responses and their intersections, or we can look at every pair of prices and find the prices where there's no unilateral incentive to deviate. Here we're going to use the second method. It turns out to be actually easier than the first method in this case, because we can divide the pairs of prices up into a small number of cases. So what we're going to show is that the unique Nash equilibrium is where they both price at marginal cost, and in this equilibrium each firm gets a demand equal to half the market demand at a price equal to marginal cost and makes 0 profit. Now unique here means that there is no other Nash equilibrium, so we've got two things to show. We're going to show first that it is a Nash equilibrium to price at marginal cost, there's no unilateral incentive to deviate, and that for any other pair of prices it's not a Nash equilibrium, there is going to be an incentive for one of the firms to deviate. So the first part of the proof is showing that it is a Nash equilibrium to price at marginal cost. So we're just showing this is a Nash equilibrium. The second part of the proof is showing there is no other Nash equilibrium. So we need to show in part 1 there's no incentive for either firm to deviate from these prices equal to marginal cost. So let's think about what's happening at these prices. At these prices, both firms are getting 0 profit. Now let's think about a unilateral deviation. So let's think about, say, firm A raising their price. Then they're going to get no demand because they'll be the higher priced firm, and so they'll make 0 profit. So this is not a strictly profitable unilateral deviation. It gives exactly the same profit as pricing at marginal cost. What if firm A lowers her price? Then she's going to get all the demand because now they're the lower priced firm. But they're going to make a negative profit because now their price will be less than marginal cost. So this is strictly less profitable than pricing at marginal cost. So neither of these deviations makes firm A better off, and so they have no strictly profitable unilateral deviation. The same argument applies for firm B, so neither firm has an incentive to deviate, and therefore this is a Nash equilibrium. Now we need to show the harder part. We need to show that there are no other prices which are a Nash equilibrium, so we need to show that for any other combination of prices other than marginal cost pricing, there's an incentive for at least one firm to deviate. So we can divide this up into 3 cases. So we have the first case here where they're both pricing less than marginal cost. So in this case, one of the firms has to be making a negative profit because one of them has to be selling something. It could be that they're both selling something, but at least one of the firms is selling something, and that firm must be making negative profit. They could do better by raising their price above C, or at least raising their price above the other firm and making a 0 profit. Then we have the case where one firm is pricing at marginal cost and the other firm is pricing at some higher level. Then the firm with the lower price is making 0 profit because they're pricing at marginal cost. They would be strictly better off by raising their price slightly, but still keeping their price below the price of the other firm, getting some positive demand and making a positive profit. So this is not a Nash equilibrium. The lower price firm could raise their price and increase their profit. Finally, we have the case where both firms' prices are above marginal cost. We're going to show again that at least one firm has an incentive to deviate. And we're going to use a diagram to show this. In particular, we're going to show that if firm B is pricing above marginal cost, then firm A is strictly better off undercutting B by a small amount than charging a higher price. So this can't be a Nash equilibrium. Okay, so in this diagram, we have a price of firm B that's above marginal cost, and we have firm A's demand curve in red. We are going to look at what profit firm A gets from different prices. So let's first look at what happens if firm A prices above firm B. Then its profit is going to be 0. Can it do better than that? Well, it can. If it prices at PB, it's going to get a higher profit. It's going to get some demand. In fact, it will get a demand of half times D of PB, and its profit will be PB minus C times half of D of PB. So in the diagram, that area is this one here. So the green area is the profit of firm A when it prices at PB and firm B prices at PB. Now what if firm A prices below PB? Let's think about just a small reduction in price below PB. So the price of firm A is PB minus epsilon, where epsilon is some very small number. What profit would firm A get? Well, now it will get all the demand because it's undercutting firm B. And its demand would be just a bit more than D of PB. So its profit is going to be P of B minus epsilon minus C times the market demand at this price P of B minus epsilon. So D of P minus epsilon is this point here. And so the profit at this price, just a little bit less than firm B's, is going to be this whole rectangle here now, which is approximately twice the area of the green rectangle. So the profit of firm A at a price of PB minus epsilon when firm B prices at PB is approximately twice the profit when firm A prices at PB. So by reducing its price by a very, very small amount, it can double its demand, and therefore its profit must go up. So an infinitesimally small drop in price is giving a discrete jump in demand, a doubling of demand in this case, and that's why there's this incentive to drop the price. So it can't be a Nash equilibrium to price greater than or equal to the other firm if they're pricing above marginal cost. So whenever one firm is pricing above marginal cost, the other firm always has an incentive to just undercut. So we can't have a Nash equilibrium with pricing above marginal cost. So this result is sometimes called the Bertrand paradox because we've gone from one firm, a monopolist, where they're pricing above marginal cost, to two firms, and we're getting essentially the perfectly competitive outcome. Both firms are pricing at marginal cost, they're getting zero profit. So the reason for this is that each firm faces an infinitely elastic demand curve at the price charged by its rival. So this is just like in the perfectly competitive model. We have this very strong incentive to undercut in this model. A small drop in price below the other firm's price is going to give a very large jump in demand. And this proof extends easily to more firms. So when you've got n firms where n can be any number greater than or equal to 2, it's a Nash equilibrium as long as two firms are pricing at marginal cost and the others are pricing above or equal to marginal cost. In any Nash equilibrium with n firms where n is greater than or equal to 2, we're going to get every firm having zero profit.